Okay, so a short video here with some hint for assignment 1 part 5, because I think this may be the most difficult part of the assignment with respect to R coding. So this is all about R coding here now. I have actually prepared a small data set here, which is same sort of type as you have, but it's much smaller. Let's have a look at it. It's the gold standard here. You can see it's only a few species and it's only a few samples. It's actually 4 samples, I think. No, yeah, 12 samples, but no, it's 4 samples. 4 samples, but there are 3 species or something like that in each sample. Yeah, so it's the same type of table, right? Except that I have made a column here called sample ID. In your gold standard tables, there is no such column, but you have a column called dataset ID, a column called group ID, and a column called replicate ID. And if you notice, the sample IDs are just this word and then these 3 pieces of information glued together with this underscore between them. So you have to create this table yourself, this column yourself, read in the gold standard, create this column, and then you can throw away all the other columns except these 2 and species and genus. We will now look only at the species, so we didn't actually need this one either, but okay, we need it for later. You were asked to do the same, first this for species and then the same for genus, so that's why I kept both. But it's this and the 2 abundances and the species that we actually need from this gold standard table. And so you can do a selection of these columns as well if you like, but it doesn't matter. You can, yeah, you choose that. The point is that what we are going to do here, we want to compare the species abundances that we have estimated to those of the gold standard, which is the true abundances. And of course, in a real life situation, you never have this table here, right? Because then you wouldn't do the sequencing at all. This is what you try to find out, right? The real abundances. But now we have, since we have the simulated data sets, we actually have the truth behind the data. So we can now compare. We can compare the abundances we get from the data to what it should have been. If everything was perfect, right? Then we should get exactly these abundances here. So we start out with the gold standard abundances like we have inspected here now, and notice this column and the species column are the 2 important ones, and all the abundances are under each other stacked like this. That's our sort of job now, to start out with our own results and try to join this into the same table together with the gold standard. So we have our estimates as a third abundance column, you could say here. That's my sort of goal now. So for each sample and species, I get an abundance value over here, which is sort of my abundances. Okay, how do we do that? Well, we have to start out with the read count table. That's where we have the sort of abundances, but they are not as abundances. It's read counts for each sample, right? Like this. And here you can see I have only 5 OTUs in this small example. You will probably have many more. But the coding will be the same. And you will have values here, right? And some big and some small and even 0 and so on. So I think that the first thing I would do now is to convert this into these relative abundances. So that instead of having read counts as integers, I only have the relative proportions, right, for each sample. So that means in each column here. So all the values in a column should be between 0 and 1, and they should sum to 1. Sum to 1. Sum to 1 for all of them. And how do we actually do that? Well, let's start out working with this read count table. And I like to make myself a temporary table here, or I just use a short name for it, where I put the results, because now things may go wrong, right? They typically do. So don't overwrite. I wouldn't put the read count table name here now, because then I overwrite it, right? So I just create a new dummy table like this. And what do I want to do with this read count table? Well, I want to mutate, but I want to mutate several columns in one go. Or I could mutate one at a time, but that will be a lot of lines of code. So I can show you how do you actually mutate across many columns. Well, there is a function called across, like this. And then first you specify which columns do you want to mutate across. And this you can specify in many different ways. Let me show you one way. Notice that all these columns start with the text sample, right? That's what they have in common. Look for things like this. What are these common? What is common to these columns, right? They start with sample, and then you can actually say that starts with sample, like this. Is a way to tell R which columns you are looking for now. And what do I want to do with each of these columns? That's the second thing I have to specify here in across. What is the function I want to do to each column? Well, I want to take the vector here, the column here, and divide all elements by the sum of all elements. And how can I specify this? Well, if you look into module 3, we actually made it under normalization there. There is a section about normal. That's what we're doing now, normalization of the data, turning them into relative abundances. And there is a small example there where we made a small function that we used in order to do this TSS normalization. That's what we are doing now, making into relative abundances. Let me show you another way of specifying that exactly same small function. You can do it like this. This is sort of cryptic. This tilde or wave here tells R that what comes now is a function without a name. This is what we call an inline function in R, or in any programming language actually, which has no name, and it's created and used just right here and then forgotten again. And what does this function do? This point here symbolizes a column now, or a vector, right? So it takes whatever column we give as input and divide it by the sum of the values in that column. So these columns must be numerical, right? Otherwise this doesn't work. But that's no problem, because we have now only selected these columns and we know that they are all containing numbers. So this should be a valid function to use on all these columns. So this whole machinery here now will go column by column by column and take the values in each column, divide them by the sum of that column. Let me show you by running this code, and before I actually run it, I have to remember to load the tidyverse packages, because all these functions here, mutate and across and starts with, these are functions that are not available unless you load the library, the tidyverse packages. So let's start by loading those, and then we can run this. And let me have a look at this TBB table now. So now you can see, compared to the read counts, it's just the same type of table. All the values changed. So now they sum to 1, sum to 1, sum to 1. All of them are relative values. So we have, like we had in the gold standard, if you notice it, they are also like this, right? All the values here for one sample, sum to 1, sum to 1. sum to 1, 3 and 3. Okay. The next thing I want to do perhaps is to stack this now, so we get the values under each other instead of next to each other. And that's something we very often do in R, and then we use this function, pivot longer. This is for stacking. And the first thing you have to do is to tell R which columns do you want to stack. And again, we could now use this starts with the sample to select these 4 columns, because it is these 4 columns we want to stack, right? And we could have done that, used exactly this construction here. Again, let me show you an alternative way of doing it, because we actually want to stack all columns except the first one. And that's exactly what we do here. We write minus and the name of the column that we don't want. And next we have to specify names too. What is this? Well, after stacking, the column names here will be put into a new column as texts, right? And here we now decide what should this name, what name should we give this new column that contains these texts. And of course, if we go to the gold standard table and have a look, we see that such texts are in a column called sample ID. So of course we also call it sample ID here, because it's the same type of information. And we also have to specify the columns, the column, the new column, where we actually stack the old columns. There will be a new column now with all these abundances under each other. And what should we call that column? Well, I call it my abundances. My abundance or something like that. So notice that you have to first say which columns do you want to stack, where do you put the column, the old column names as texts, and where do you put the old values of whatever they may be. So let me run this now and see how it looks like after stacking. And now you can see that all the sample ID names are now under each other here, and they will appear. If I click here and sort it, you will see this is appearing now 1, 2, 3, 4, 5 times, because there are 5 abundances in the first sample for these 5 OTUs. And then sample 2 here, 1, 2, 3, 4, 5 times. The 5 abundances for the same 5 OTUs. So the OTUs are now listed over and over and over again. And this is exactly the same type of data. It's the same data we had before stacking. It's just rearranged, right? There is nothing has been lost, nothing has been gained. It's just a rearrangement. But now we can see we have column here and a column here, which is sort of similar to what we had here with the abundances. So now we are approaching something. But there is one piece of information we are lacking here, and that is the species name, right? We have the OTUs, but we need the species name of each OTU. And that is something we have in this sequence table, right? Here we have the OTUs, and if I go out in a column out here, here we have the species names that we got from the taxonomic assignment using the syntax, right? Except for this OTU hasn't gotten any species. It has a too low score, right? But this is fine. We will have to deal with that. But a species column we have. So this column together with this column is what I need from this table here. And I need now to join this with this table here. So for each row I have OTU1 listed, I want to have the corresponding species listed out here as a new column. And then for OTU4, the OTU4 species, right? OTU2, OTU2 species, and so on. How do I manage that? Well, left join. Sorry, I took away some parentheses there, I think. There. Left join is a function we often use. And that means we take this table that we have produced down here and we keep that fixed. And that's this one, right? This one should be fixed, and then we sort of put in new rows here that we get by joining it with this sequence table. So the sequence table is the table that we take information from, you could say, and then we keep this table fixed. But we don't want to import all the columns from this table because we only needed the first one and this species. All the other ones here, well, yeah, it's a hassle to have them, right? Because we don't need them. So I actually want to take them away. And how do I do that? Well, I do a select on this table now before I join it. And I can do it in the same line like this. From this sequence table, I select only the two columns, header and species, like that. So you can see this piece of code here as a change of this sequence table where you only pick up these two columns, and then I do the joining and use the header column as the joining information. Like this. Let's try and run it again. Yes. And now you can see this column appeared out here. And for each OTU, we now have a species name. So in order to be able to join this with the gold standard, I see there are a couple of things I have to do. First of all, this one here doesn't have a species name. Okay, then I have to just discard these rows because I don't know which species they are, these OTUs. So that's the first thing. Take away these rows where you have missing values on the species. And then I can also see that the species names, they have this S underscore underscore, and they don't have that here. So in order to match them, I have to prune away this at the beginning here, right? This is something that comes from that database that we used in the syntax algorithm. So these two operations I will do now. First, take away the NAS, the rows where we have NA under species. That's this function will simply filter out these rows. And then I also say that I want to change or mutate the species column. The new species column should be the old species column where we have removed some text. And still remove will remove some text. And it will remove from the old species column. And what text should be removed? S underscore underscore. This is what I want to remove from every text there. So now you can see the table looks pretty. Now we have names that are corresponding to the names over here. It's not exactly the same. I mean, sorry, let me click away this too. For instance, E. coli is only here. It's not E. coli over here. And perhaps the other way around as well. There are some names lacking in both ways, but that's something we will have to deal with. Before I do the joining here now, I should be a little bit looking a little bit more carefully into this table, because notice here that OTU2 was classified to this species here. But OTU3 is also the same species, isn't it? This is the same one. So now I should actually summarize the abundance. I mean, I have the abundance for OTU2, and I have the abundance for OTU3, but these are the same species. So I should add them together because I want one abundance for each species, right? And how do I do that now? Well, I noticed that if I sort of group by species, and by sample, then I should be able to sum these values, right? Because, for instance, this one here, OTU3 sample 100A1 has an abundance for this Olea species. But OTU2 up here, for the same sample, also has an abundance for this Olea species. So I should actually now group by this column and this column and sum up the abundance of this column. Let me show you how to do that. Group by sample ID and species. If you want to group by two columns, you just type them like this. And then I do a summarize of the my abundance being the sum of my abundance. So the new my abundance will now be the sum of the old ones, where we have grouped the rows like this. So in those cases where we only have one row for each group, nothing will change, of course. But in those cases where, in these particular cases for OTU2 and 3 will now be joined. And notice the header column will now disappear because we don't do anything to the header column in the summarize. The summarize function will only keep the grouping columns together with those that you summarize. And it's also usually a good idea to end this with ungroup, like this. So you take away this grouping information again. So these three lines here sort of belong together. So let's see what happens now if we run this code here. Yeah, you always get this output here because of this grouping. So let's have a look at the table now. And now I think we can see that, yeah, now you can see for each sample here now, sample 100A1, 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 there is only 3 species here now listed, right? And the same for sample 2 and B1 and B2. So now we have sort of joined together. And if we compare this to the gold standard, we have actually exactly the 3 columns we need. The sample ID, species, that we also have here, sample ID and species. And we have this my abundance, which is now. So if we now just full join with this gold standard table. And why do I use full join this time? Why not left join? Well, remember what left join is. The premises for left join is that the first table you then keep fixed and you just add information from the second one. With full join, none of the 2 tables are fixed. You keep all information from both tables, right? And that is exactly what I want here, because it's not like one of the tables are sort of more important than the other. This is a case where I want to keep all information from my abundances and all information from the gold standard table. And that's why I use a full join. And I have to say, where is the joining information? Well, it is both sample ID and species. Otherwise, you will get a lot of combinations. So, sample ID and species, like this. Both must be used in order to put the correct rows from one table together with the correct rows for the other table. And now we can see here, yes, for sample 1 we have this species, it has my abundance like this, and it has a gold standard abundance like this and like this, right? This species here is only in my abundance and is missing in the gold standard. And this should now be replaced by zeros, because a missing value here means that it's not, it has abundance 0, right? It's lacking, it's not there. And this we will see again, right? E. coli comes again here, and down here we have it the other way around. For instance, this streptomyces species here is not found in my abundances, but it should have been because it's in the gold standard. So here, now it's these we have to put zeros in, right? Let me show you how to do that. We simply use mutate again, and for instance, my abundance should now be mutated. And how do we do that? I use the if-else construction. That's a very nice one. I say that if we have an NA in this column here, this one will just go through the rows of this column and return true if it's a missing value or false otherwise. And if it's a true value, true, it means it's a missing value, then I should replace it with a 0. Otherwise, I leave it as it is. So this is how this if-else works. It performs a conditioning on this vector here. And for each element, you get either true or false. And for those elements you get true, you put in this value over here. And for those that get false, you put this value over here. So you see in the latter case, nothing changes. It only will replace NAs with 0. Yeah, you can do this replacement in many different ways in R. This is only one of them. But I like to show this if-else construction. So let me now put my cursor up here again and run this code one last time. And then you can see I've gotten zeros here. And now you can do exactly the same for this column and for this column as well by mutating them in exactly the same way here by adding 2 more lines of code, and then you have the table you need. And then you can start plotting these values against these values to see if they correspond to each other, and you can compute correlations between them, or do the same for these values against these values over here. And then you have the comparison that this exercise was asking for. And of course, if your data set was perfect, your processing were perfect, your taxonomic classification, everything was perfect, then the values you get here should be exactly the same as the values you get here. Perhaps not here though, but here it should be exactly the same. But it will not be, I can tell you, because nothing is perfect, right? But now you can see how far from perfect it is. Okay.